but I will get that in. But there is one thing that I do want to do. I would like to do in class before I leave chapter 3, and that is area under a curve. So oftentimes in physics, there are physical quantities that we can represent graphically, and when we graph something, whatever kind of function it is, whether it's a constant function or whatever, the area under the graph between 2 points can represent another physical quantity. We'll see that probably 4 times throughout the next 3 courses, including this one. But this is the first time that you see it. And if you realize that, then you can use a graph to actually determine quantities, things, variables and quantities without having to do it quantitatively. And sometimes that's helpful. Sometimes if you don't have enough information, you can use a graphical representation to basically get implicit information that's implied by the scenario or the situation, but it's not stated. Ouch. All right, so area under a curve. I'm going to graph the velocity versus time. We've been looking at displacement versus time a lot, but here, this is velocity versus time, and we developed the equation of motion, so we know that it's a linear equation. Remember, when we looked at accelerated motion, we said there were 5 equations. Velocity with respect to time equals initial velocity plus acceleration times time, and then the other 3. Well, if I plot, time as the independent variable and velocity, v of t, as the dependent variable, this is a linear function, right? Y of x, as long as the acceleration is constant, this is a linear function. Y of x equals b plus mx, or mx plus b, right? So the v naught is the independent variable, is the y-intercept. The acceleration is the slope, and of course, the t is the independent variable corresponding to x in the point slope formula. I think that's the name of it. Whatever. Actually, that's the equation of a line. The point slope formula, I think, is where you take the m and you do the y minus y1 over x minus, or, well, y. What? Yeah, 2, 1. Let's just do that. And 2, 1. I think that's actually a point slope, isn't it? I don't know. Anyway, you know what I'm saying. This is just a different version of that, but written in terms of independent and dependent variables, where this is written in terms of difference in the points and the slope. Whatever. Point is, this thing is a linear equation. So if you graph it, a very simple graph of this equation looks like this. Looks like this. V, V, and this line represents this curve, this function of velocity. So this guy here is V of, this is the function, right? This is this graph. And so you're saying you start at some initial velocity at time t equals 0, the thing is accelerating, and so you can look at the increase in the speed at 2 different points, say time t1 and time t2. So t1 is here, t2 is here, corresponding to speeds v1 and v2. more specifically, v at times t1 and v at times t2. That's what this means. So this point here and here are going to correspond to um, the velocity at time t1 and the velocity at time t2. Okay, you see that? Now, what I want you to do is just focus on this part right here. So this is the curve. We're going to look at the area under the curve between T1 and T2. In fact, let's go ahead and calculate that. Calculate the area. Find the area. So this is a little quick exercise. I want you to figure out what the area is under that curve and then see if you can relate it to some physical quantity that we've studied. That is, determine the area. Under the function v of t between determine the area under the v of t between t2 and t1, between t2 and t1. Yeah, that's it. Determine the area under the curve v of t between t2 and t1. Oh yeah, and related to a physical quantity. That result to a kinematic quantity. Okay, so how would you figure out the area under that curve? Well, you could integrate. You could do calculus and do it, but I'm not going to do it. That, as I said, we won't, because that's what you're doing when you're integrating, right? You're finding the area under the curve. When you're differentiating about a point, you're finding the good. You can integrate. But I promise you, as I said a few moments ago, we're not going to lean on the calculus just yet. And with this one, it's a linear function, so we don't really have to do integration. That would actually be more than what's necessary to figure out the area. We don't have to do that. We could, we should give us the same answer, but you probably did something like this in high school where we could break this up into geometrical figures that are figures that we know how to we know the formulas for the area. That is, if I kind of take a horizontal and project it across here from the point of V1, I can break that whole area up into two shapes. One is a rectangular shape here, and the other is a triangular shape here. So if I use my formulas for area of rectangle and triangle, I can find the area of that thing without having to integrate this function between T1 and T2. For those of you who would like to, we'll do it this way, but if you want to go ahead and test yourself, your calculus, and integrate that function, you could do that, and you should get the same answer. But I'm not going to do that in class just yet because I want to move it along, and we'll get to a point where we'll be doing plenty of integrals. That's later on. So yeah, the area of a triangle is length times width, right? The length is whatever, is delta t1 minus t2. The width is basically v naught. No, sorry, the width is 0 minus v of t. So the height of this portion is just v of t1. Here, the height is v of t2 minus v of t1. And well, and it's a triangle, right? So the area for a triangle is 1/2 base times height. So you go 1/2 of v of t2 minus v of t1 times delta t2 minus t1, of course, times 1/2. And so then you add those two areas together and do the algebra, simplify it, and then see what you get. So what I'm asking you to do is, you could add area, the area of the triangle. I don't know how I could do this. Area of the triangle plus the area of the rectangle. And yeah, just start there. And then see if, when you get the final answer, if it'll look like something you know. Give it a couple minutes, like a minute or two, and then I'll come back and do it. Cool. Did anyone get a result? And can you tell what it is? Anybody? Kevin Cox, did you get a result? Kevin, you there?
Here, I can share. I don't know if it's right though, but I got some things.
Okay, give it a shot.
So it's kind of long. I didn't really like simplify it or anything, but so I got area is equal to T2 minus T1 quantity times V of T1 plus 1/2 T2 minus T1 times V of T2 minus V at T1.
Okay. And that's as far as you got it to simplify?
Yeah, I didn't simplify it or anything. Like that's just like straight up.
Okay. Actually, it sounds like you might have gotten it. I would need to I need to simplify to see, but let's take a look. Sorry, there you go. Yeah, so area of the rectangle is T2 minus T1 times basically BT1. So T2 minus T1 times V at T1. I think you said that. Then plus 1/2 times the base. The base we could still say is T2 minus T1. And the height then is going to be these guys, V of T2 minus V of T1. And that's got to be in parentheses itself. So I think that's what you wrote, what you stated. Let's simplify it. So when we put in the V of T, we're putting in this thing with those particular times substituted in, right? So this thing is going to be, we still have T2 minus T1, but V of T1 is this, V naught, or times V naught, plus A times T1, because that's what we put in V1. So A times T1. Okay. Plus 1/2, again, T minus T1 But this thing comes the difference between those two with the t respective t's placed in. So this is going to be, I'll put in brackets, v naught plus a times t2 minus v, I guess, quantity v naught minus a times t1. A lot. All right, so now let's multiply through. I think I'm doing this right. Done this in a while. Yeah, I think it's gonna work out. I guess I could have made it delta t. That would have been probably easier. But, well, actually, no. Let's just do this. So yeah. So we're gonna have, well, we get 4 terms out of this. We get v naught t2 and minus v naught t1, and then 2 terms here. It's going to be plus a times t2 t1 minus a times t1 squared. That times that. This guy, this is this guy, these two here, and this is here, yeah. Okay, now let's work out this stuff first before we multiply. So we got t2 minus t1 over 2 quantity times bracket stuff. And the bracket stuff is going to be, well, yeah, so v naught minus v naught goes out. Let me just put it here. Minus and minus is a plus. So this cancels. And here I've got basically plus a t2 minus a t1. So I'm going to get 4 terms out of that thing. And the 4 terms, I'm going to leave the half out for now. 1/2 times this guy is going to be a t2 squared and then, you know, this guy times this guy is a minus a t1 t2, and these two are going to be minus a t1 t2, and then these guys are going to be plus a t1 squared. And all of that's times a half. So if I bring the half through, it's going to be half there, half there, half there, and half there. Okay, yeah, we're making a little bit of progress. Now watch this. These are the same values, right? It's 8, 2. That's going to be a problem making it. Well, actually, once you see if you can simplify, and I'll I fix something here. I was pointing out that this is AT1 T2 over 2, AT1 T2 over 2 minus. So you add those, you get one whole. So you have a minus AT1 T2 from these two terms. But here you have a plus AT1 T2. So they cancel. So this guy here cancels with both of these. Seems like I still got an extra term in there somewhere. I don't know. Trying to work ahead in my head. Let's just do it. So here, what's left is a V naught times T2. Oh, right. I see why it's different. Why I have much more terms, because in my notes, I just went from T equals 0 up to T2. That's why. That would have been easier. But this still should work out. So let's just see. That's why it's different. And so I have a minus V naught T1, minus V naught T1. And here I have a times T2 squared. Yeah, I think I screwed this up. Yeah, it's easier if I extrapolate T2. I could just do that. Take T1 back to T to 0, like extrapolate. That would be the whole thing. I might do that because I think it's going to be a little bit harder to see the point the way I'm doing it here. But let's just go out and finish out and see what we get. So then this is a minus a T1 squared. So then I have these two terms here. I have a plus a T2 squared over 2 and a plus a T1 squared over 2. So yeah, so just yeah. So this right here is equation 5. So yeah, so now those last two terms over there, shouldn't that be minus? Is T1? Well, why are you adding it? And then T1. You know, T1. That goes to 0. That goes down. I can take these two terms, and that's going to be V naught times T2 minus V naught times T1. And then this thing, oh yeah, that's why, yeah, good. So so it'll work out. AT1 squared, so minus AT1 squared plus AT1 squared is a minus, so sorry, minus AT1 squared plus AT1 squared over 2 is a minus AT1 squared over 2. So adding these two terms, they'll go out, and what's left, these two right here, and what's left is a minus AT1 squared over 2. And that'll do it. So I have a minus a plus AT2 squared. That's just still there, just write that down. Then a minus a to T1 squared over 2. Yeah, so here I just factor out everything. So I can factor out V naught from both of these terms, V naught T2 minus T1 plus basically 1/2 A times T2 squared minus T1 squared. Now, because I chose to not make it like this, it probably might not look too familiar to you, but does anyone recognize what that quantity, that whole quantity is? Anyone? What about if we extrapolate that T1 goes to 0? Basically, T1 goes to T naught, which is equal to 0. If we had done that, then basically, well, actually, yeah, if we had done that, then it would have been this whole area like if T1 goes, basically V1 becomes V naught. Maybe it would be easier to see that. In the limit that T1 goes to T naught and basically 0, then this term goes out, right? That term goes to 0, that term goes to 0. And what I'm left with is under that limit, V naught times T2 or just T plus 1/2 A times T squared. That should look a little bit more familiar. What is that? What is that quantity? Vincent Chang? What is that? This quantity right here. That look familiar from an equation of motion that we derived the other day? Come on, somebody, tell me. Am I missing?
It's
It
on one of
does
those
look
tables.
familiar.
Kimberly, go ahead first. I can't hear you both.
I said it's on one of those tables that you gave us. I think the first one.
Yeah, so which equation? What is it?
I don't have it. I don't even have it. I don't have the data like in front of me, but
Oh,
I just remember
okay.
it being like on one of the tables.
It was. So was it? I didn't hear. Somebody else was also talking. I couldn't see who it was.
Yeah, I was talking. I said it does look familiar.
Oh, number 14. Okay, he said it.
In the chat. Yeah.
Oh, in the chat. I'm trying to get back to the chat. I can't really see it. I got a different view on here. Somewhere. No, exit full screen. Okay. There you go. It's number 14. You mean equation 14? Arcady? Are you looking at the equations?
Yeah.
Yeah, equation 8. Yeah, it's not an equation. But it's associated with that equation. But still, it's not. It's just the area. Like so, it's not. I haven't. Look. There's no equality there. So I guess what I'm asking is, if you look at that equation, what part of that equation is it? What does it represent physically? In that equation, what does that part physically represent? And actually, I'm not sure that it was equation 8 or 14, the way that I wrote them down. I think it's more like equation 3 and 5, 3 and 8. Yeah, it was equation. Someone did say equation 8, 3, 8. And also in the free fall motion equations, it would have been equation 12, actually, not 14. in the way that I wrote them down. So no one knows what the physical quantity represents then.
Represents the area under the curve.
Well, that's mathematically what it represents. I'm asking physically what it represents. It is the area under the curve, but the area under the curve represents something physically for a problem that's accelerating at a constant acceleration, you know, with these different initial and final speeds.
Does it like
And you can tell.
Sorry.
Go ahead, Mikey.
I was gonna say, does it represent like the change in velocity, so it's like acceleration, or is it something else?
No, it doesn't. But you said change in velocity, you said change in acceleration. There's not too many other kinematic quantities that we have, so keep going.
Change in speed.
Change in speed and change in velocity are related.
Change in
so no.
time.
Nope.
Change in distance.
Change in position.
Okay, and this
There you
this is
go.
becoming a guessing game right now.
Well, it's a process of elimination, so that works too. And the last two people said it. It's the change in position, and that actually has a name. What do we call that?
Distance.
Displacement.
Well,
Displacement. Yeah, displacement.
that both correct. That distance is the high school version name of it. We want to level up. So yeah, the quantity that I'm looking for in the name it's the displacement. It represents the displacement of the particle moving along with, you know, a velocity that's defined by an instantaneous velocity defined by this equation. Yeah. So what we say is that the area under the v of t curve, the velocity with respect to time curve, is actually, right, this is v of t versus t, if I were to name it correctly. The area under that curve is actually represents the displacement of the particle as it moves with that, you know, moves with a motion that's defined by that velocity equation. Yeah. So to illustrate that, for those of you who didn't see it or may still not see it, let's just write down one of those equations. So that equation was, the one I'm referring to is this guy, that x equals x naught plus v x naught t plus 1/2 a t squared. So again, I think in the notes, that's equation 3, 7, and no, 3, 8, and 12, the different versions of it. And if I take the x over to the other side, I have x minus x naught, right? Which is equal to delta x, the displacement, and that's equal to v x naught times t plus 1/2 a times t squared, which is the thing that we just derived. So yeah, so that's probably one of the first time. I think you've probably seen this before. I know you have in calculus, but probably because you were focused on the math, on the calculus, and integration stuff. I don't know if it really registered. But yeah, and it doesn't matter that this is, even if it's not a constant. So let's say we have some other kind of function. Maybe the acceleration is not a constant. And, you know, you have some velocity that's where the acceleration is changing, right? Because remember, the slope of this curve is the slope of x versus t is velocity, slope of v versus t is acceleration. So this represents a constant acceleration. That's what we just said, it's linear. But what if in v of t, you know, you got some funky thing looking like that? That means the acceleration is not changing. Still though, the area under the curve should be, you know, should be the displacement. But how do you get that? Well, you have to integrate, right? You have to integrate that function, and the integral of that function will give you the area, as I know you know that. But now, you know, in terms of v of t, it would represent the, so that's one way of getting it. And honestly, that's a valid problem for this course. That's what I mean. Like, I'm just not focusing on that intensity of the calculus just yet, because I want you to get the kind of more qualitative stuff associated with kinematics. But we could jump to a problem like that, right? Where we just start integrating, and but we'll get to things like that. Yeah, V of t versus t. Yeah. What am I doing? I just lost my train of thought. Yeah, so that's what I wanted to do. So that's the end of that. What I have here, that's the area under the V of t curve graph gives the total displacement, x of t, internal position, as is known, and like the area under. Mm. Oh yeah, right. Yeah. So let's write down qualitative. Write down in words what we're saying. Yeah. So what we can say is that the area under the V versus T curve gives the displacement provided that the initial position is a given. So no, it gives a displacement, and you can find the final position x of t if the initial position is known. Therefore, the displacement delta x, and because of that, x of t, the final position, may be determined if if um, if x naught is known. And I'm not going to draw the graph and have you do it, but even we could also say something similar about the A versus T curve. Right? If I graphed A of T versus T, whether it's constant or not, the area under A of T versus T is it doesn't really have a name, but just delta V. And so therefore, if the initial velocity is known, one may find V of t, because obviously V of t is going to be equal to V naught plus delta V, right? Because by definition, delta V is equal to V2 minus V naught. And same thing here, x of t is equal to x naught plus delta x. That's how you would find it. So, yeah, you could use that information to find, those quantities, Vx naught or x of t or V of t, in that way, without having to manipulate equations of motion. All right, that's area under a curve. Not quite break time yet, so let's just regroup here. Oof. Hopefully you can see that. What I'm writing here is since delta x is defined as V of t minus, x of t minus x naught, then x of t, the final position, is going to be equal to x naught plus delta x. And similarly, delta v is defined as V of t minus V naught, V final minus V initial, where V final is going to be the velocity at any arbitrary time. Then V of t equals V naught plus delta V. That's what we're saying. Looks like that might be coming from school, so I'm going to take that. Okay, I'm sorry, I apologize. Not sure what that is. Oh, it went out. I'll answer that during the break, I guess. The 323 number, so it might have been coming from school. Guess I'll get a message. Yeah. Yeah, so that's area under the curve. And yeah, so that's the what I wanted to cover that in class prior to going to two-dimensional motion. So yeah, so let's shift gears here and I'll set up two-dimensional motion before we go into our break. Basically, what I'm going to do here is kind of derive it's kind of the same thing, right? We look at position and displacement in 2 dimensions, and then derive the equations of motion for parabolic motion, and show how they are a combination, basically, of general motion in x, but constant motion in the horizontal plus the free fall motion equations. We show that, and hopefully, and I'll be able to get them derived for the parabolic equation, parabolic motion equations derived for you, so that you'll have that over the weekend. All right, so let me. Yeah, I definitely got something going on there. Actually, you know what? This probably is. Let's do a little bit of an early break right now, because I have a feeling this might be some administrative stuff coming from school. So we break a little bit early. We got 15 minutes before the scheduled break, and so I can maybe figure out what's going on here, and then I will get back to you, and then we'll come back. So let's take a 15-minute break, whether that be. Actually, let's take 20 minutes. I might need a little bit more time. So maybe we'll come back at 2:35. Cool. How about that? All right, let's look at two-dimensional motion. What we got here? Starting with yeah, you know, it's like, you know what a vector is, right? We've been looking at one-dimensional motion, but actually, if I have a vector I can represent it in 2 dimensions or 3 dimensions. Yeah, so like if I have now be careful, like the graphs that I've been showing you previous up to now, they have been X versus T, V versus T, A versus T. I mean, I didn't explicitly show A versus T yet, but in that last curve, I kind of illustrated so we're talking about time being the independent variable. But the first graphs that you looked at, which you look, it was like y of x. So that x, it was space. It was y on the vertical axis.
Yeah, I feel like he's really cutting up.
Am I? So let's see.
Yeah, I can't really understand like that word you're saying, to be honest.
There's a latency. It's not really cutting up. It's just a latency. Like you say something and it takes a little minute for
Yeah,
for
that
us to hear
happens.
it.
I don't know if I'm gonna be able to fix that. Okay, yeah, I'm not sure how to fix that. It happens with the signal sometimes.
I think it's good right now.
So maybe I could. Okay. All right, cool. All right, so yeah, I was saying that the first graphs that you were given are graphs in space, so like x versus y versus x. Right? This is back in high school, middle school, whatever. All right. So you got x along the x-axis, y along the y-axis. Am I still? How is the
It's
signal
pretty good
now?
right
Is
now.
it?
It's
Okay,
pretty
good.
good right now.
All right, cool. All right, yeah. So let's go back and take a look at that type of graph. Make that straight. let's say that we have an ant. An ant is crawling along this board. So they're crawling along in two-dimensional space, right? And it might map out a specific path. And that path, you know, it's just arbitrary, but it might look something like this. Actually, let me make this bigger. So you map out a specific path, and the path might look like this. Just crawling along arbitrarily, just doing whatever, I don't know. Something like that. And let's take the guy, so and it's moving, this arrow denotes the direction of the path of the object walking along, of the ant walking along. Now, what does position look like in two dimensions? Well, this is the origin, and the position is based, you know, like when I did last week, when I showed you the one-dimensional case, it was like a number line, and we showed position, displacement, just along, you know, a linear direction. But here, we have to represent the position in space that is represented by an area, a length times a width, not just a length. And so we do something similar. We just take a line and draw it, like say if at some point in time, the particle or the ant is at some position, say right here. Then to represent that position, we draw a line from the origin to that position on the path. And that line would look like this. We call it R. Where technically speaking, R in general, in calculus, you learn that R has three components. R is defined as, I might have written this last week too, I don't know. But let's just do it now. R is equal to a component along the X direction, plus a component along the Y direction, plus a component along the Z direction. But in this case, the Z direction is, the value is 0, so that means that the vector is just in the XY plane. In other words, if the Z were not 0, what would this look like? Well, the Z direction, if X positive Y is up, positive X is to the right, positive Z is out of the board here, moving toward you. So a three-dimensional vector would be represented by an object still pinned at the origin, but projecting out into the room, right? So if the Z component is 0, that means that the R vector is going to exist only in the XY plane and just have components that lie in that plane. Essentially, that's like the projection of the three-dimensional vector onto the board, and that's what this line represents. A two-dimensional vector that has no Z component. Let me say it a different way. Let me open this light. It probably put a little bit of a glare on the board, but maybe it's better if let's not put a big glare. I think I got a flashlight over here somewhere. Let me go get a flashlight. Basically, I need to define to you qualitatively what a component is. I've been using that terminology, but only describing it mathematically. Let's describe it a little bit more qualitatively, subjectively. And that'll make this these vectors here make a little bit more sense. Actually, you can see my, oh, actually, you know what? I don't need a flashlight. I can just use my light here, the light that I'm using for the board. Actually, well, you can kind of see the shadow there. It's better if yeah, because it's gonna, let me turn this off for a minute and maybe do the flashlight. Because I have a little bit more control over the direction in which, is that gonna do it? You know what? Maybe this is better. Yeah, I think you can see the shadow a little bit better there. So you see the shadow as I go in, right? See the shadow back here. So that's why I'm saying that this shadow is actually the projection of this three-dimensional figure onto a two-dimensional space. In fact, if you define the term component, just kind of making up my own definition in my words, a component is a projection of a higher dimensional object onto a lower dimension, the next lower dimension, well, onto a lower dimension. So a component. Let me do that over here. Component. A projection of and a component is a projection of an object from a higher dimension onto a lower dimension. Of the object or a quantity said differently, a projection of a higher dimensional quantity onto a lower dimension. In this case, the quantity is representing the length. So if we have, this is a meter stick, right? And again, it's not really, I would really need to have what we talk about, the projection that's most important in physics are going to be the perpendicular projections, meaning if we're right at the tip of the object. So you can see here that, right, because this light is casting a shadow at an angle, the direct light is directed at an angle, it's going to, if I were to take a line and draw it directly from the light beam past the tip of this object on the direction that the light is traveling to the board, it's going to hit the board at an angle that's not 90 degrees. So I'm still getting a projection, but it's a projection that is not a right angle projection. When we deal with components in mathematics, we want right angle projections, meaning if I were to take this light and place it such that the light is passing directly past the tip of the meter stick, it's going to project back such that that projection makes a right angle with the surface upon which it's projecting onto. So if I were to do that, that is what I'm referring to as component, and what we generally refer to as a component in mathematics. Although in general, even if I don't do that, as long as I'm projecting onto the thing, I am getting a component, but it's not a right line component. Well, what happens when you do that is you don't get all the information a lot of times. Meaning, or sometimes the information can be skewed. You can see now that the length of the shadow is much longer than the length of the meter stick. So the projection, sometimes information is lost or it's skewed. It's not really representing really the entirety of the object. Another way to think about it is, what if I had two-dimensional people on the board? So let's say I have a guy here and he's looking at the, so this is a two-dimensional person, and they're looking at the shadow that I cast. Well, the shadow, you can see it here, doesn't have all the properties associated with the meter stick, right? The meter stick has, dimensions, increments on it that are labeled. It's three-dimensional, right? It has a thickness. This two-dimensional person, in fact, they can't really even see the width from the perspective that we're still looking. What they would see is just a line that looks something like that, right? They would just see the edge, one edge of that projection of that shadow. And so, they don't see the color of it. They don't see the thickness, the dimension. So that generally is what happens with components. You don't necessarily see all of the physical aspects of the object once it's projected back onto the lower dimension. But it's a representation of the higher dimensional object onto that lower dimension. I think my earpieces are to go out. I need to go get another one real quick. So let me do that. All right, testing. Can you hear me? Testing.
Yep.
Is it connected? Good. Awesome. Yeah, so let's move this along. Yeah, so what I'm trying to say is, so in this last example, this class demonstration, I had a three-dimensional object projected back onto a two-dimensional surface. Here, I'm starting with a two-dimensional representation of a vector, this guy here. So what does it look like when I project it back onto a one-dimensional line? Specifically, the one-dimensional x-axis and the one-dimensional y-axis. Well, you've seen a drawing that illustrated before. It looks like this. We call it dropping a perpendicular. So it'd be kind of the same thing as if this were a physical object and I took a flashlight and I shined it down so that I find the perpendicular. I projected along the perpendicular distance below the tip of that vector. Then this guy here represents the projection of that two-dimensional figure onto the one-dimensional line. So that would be X. the X associated with that R. So the magnitude, the length of that shadow, that projection, is the magnitude of the X component of that vector. And its direction is represented by the unit vector, which we talked about on the first day. So here I don't necessarily have to put the unit vector there because the X, it's implied that it's along the X-axis. So I just need the magnitude. And same thing here. If I project the perpendicular distance back to the Y-axis, that's going to give me a visual that represents the Y component. That is the magnitude of the vector projected along the Y-axis. And so obviously we're losing some information because this X is not completely, you can see that it's shorter than R, and Y vice versa, and similarly Y is shorter than R. So that's what I'm saying. In this case, I'm projecting the quantity length back onto each of the respective axes, and I'm not getting all the information, right? Some of it is lost, but I do get a representation of the length of the vector R onto the X and Y axes, respectively. Now, we will ultimately show that we can use geometry to define the components in terms of the others. We'll do that eventually, and using trig, cosine, sine, that sort of thing. But right now, we'll get there. We'll get there, a little bit later. Right now, I just want to define that, what a position vector is. So this vector in 2 dimensions represents the position at a particular time of this ant moving along this path. And so we can box that in as a position vector. Now, technically, we do this in 3 dimensions, as I said, but just to make the mathematics simpler, and because ultimately we're talking about the same thing, we're just going to focus on 2 dimensions, right? 2-dimensional motion right now, because whatever equations we define or derive in 2 dimensions, we'll have similar ones in 3 dimensions. It's just that it makes it more cumbersome. So it becomes more of an algebraic record keeping. And right now we want to just, the way it's usually done conventionally is that we just describe 2-dimensional motion because we want to focus on the physics and not get bogged down by the notation and the algebraic manipulation of dealing with the same. Basically, the physics doesn't change in 3 dimensions, but the algebra gets a little bit more cumbersome and can kind of distort focusing on just the physics of the motion. So yeah. And oftentimes you do see the unit vectors portrayed down here at the bottom. I think I said that the other day. That would be the I direction. We don't normally do that, but just the purpose of illustration, I will. And this is the J direction. So you can always represent the unit vectors as a value of 1 unit down from the origin. And so this vector would be, this is a pictorial representation of this equation. So that's position in 2 dimensions. What about displacement? What does displacement look like in 2 dimensions? Well, displacement implies that I move from one direction, to another point. So here, you know what? Let me draw it again. Let me draw a different curve. I'm going to use this guy. Okay, sure. I don't want to make the picture messy. A little bit messy. Let's consider snapshots of this ant moving along. So at one snapshot, t equals time 1 is the guy's here, and maybe sometime later the ant is over here. Yeah. Oh no, like here. All right, so I'm going to draw the different snapshot over here somewhere. Try to recreate the graph like so. Not going to be an identical path, but the best. Go something like this. I don't know if you made all that noise. I'm making it. But still, there we go. All right, so sure. Let's say that, so maybe the first position is like somewhere like right here, right? There. Something like that. And then at a later time, the guy was over here, maybe at the tip there, tip of that thing. And we'll label the position mark. So this is R1. And it's the same, this is also R1. And this guy here is R2. Now, both R1 and R2 have their own, their own components. Should I have made it a different color? Yeah, why don't I do that? I'll make this a different color. Let's make it green. R2. So project down here, we got X2. And here we got Y2. And over here we got X1 and Y1 like we showed before. Okay. Now, a displacement is defined as a final minus initial. So using the definitions and the notation that we've used previously, right, a displacement versus a position is really a difference of two positions. It's delta R, which is whereas R represents position, delta R represents displacement, and delta R is defined as R2 vector minus R1 vector. Okay. Now I haven't actually shown the displacement here. What I want to do is calculate it, quantitatively first. Then I'm going to come back here and show you how the delta R relates graphically to R1 and R2. And also it's showing how the components relate. But let's first figure this out first. Let's move through and apply the definitions, the basic definitions of mathematics, what I just showed here, the definition of R, put that into this formula, and then calculate what delta R looks like in terms of the components, delta R. Okay, let's do that. Okay. So R is this guy, so then R2 is going to be, as I said, so delta X, let's number the equation. So equation 1, 2, 3, and 4. Okay. So that delta R is equal to, well, R2 is going to be X2 I plus Y2 J. You don't need to put subscripts on the unit vectors. Quantity minus X1 I plus Y1 J. Okay. Well, let's do the algebra. Let's just distribute the minus sign. We get 4 terms, X2 I plus Y2 J minus X1 I minus Y1 J. Okay. Let's then, associative property, group stuff together that has the same, that's because, like with a vector, why do we have to do this? Because you can't add vector, you can only add quantities that are along the same direction. So like if I knew the value of R, its magnitude, and the value of R2, R1 and R2 respect, I just can't add them together. I can't add their magnitudes because we have to also consider direction, right? You with scalar quantities, you can just add them up like you did in 4th grade, 5th grade, whatever, because you don't have to worry about a direction. But here, you have to also consider the directions of the object. So what we basically have to do is break it down into the components so that we can add the magnitudes of the components, because the components do lie along the same coordinate direction. They don't necessarily have to be in the same direction. They can be opposite, but if they're along the same coordinate direction, they can be added. They can be added. With the and so that's what I'm doing here, kind of quantitatively. So we can group together the quantities that are along the same coordinate direction. So x2 is along the I direction, x2i and x1i are. So putting them together, I get x2i minus x1i, and grouping y2 and y1, I have plus y2j minus y1j. Now, factoring out an I, forget what the property that's called, maybe it's still associative, x2 minus x1 quantity I hat plus y2 minus y1 quantity j hat. So ultimately then x2 minus x1 by definition is a delta x along the I direction plus a delta y along the j direction. And now we can see that what the components of R are. That the components delta R also have components delta xi and delta yj. So Kimberly, was that a question or? So what is the question? I can't quite make it out.
I just wanted to be sure. So we gotta add them on the end when we adding vectors, right? We gotta add them on the end. We can't just.
What do you mean by add them on the end?
Like we can't just add them any kind of direction. Like if they facing toward each other, we need to add them like from one end to the other, like that. You know what I mean? Like
Not quite. Oh, I got you. I think I do know what you're talking about. Yeah, that's like so yeah, that's one, yeah, that's right. That's one where you're talking about relative. Well, one way that's probably done is something called relative velocity. So like you have a vector A, right, that's pointing like that, and you have to have a vector B that's pointing like that. You put them together, right? Then you have A, like, because you can move a vector around as long as you don't change its angle or stretch it or shrink it, you can move it all over the vector space. So I could kind of move this over here to this side, like project it over to B like that. Right. And so now I have them together, and A plus B is, A minus B, A plus B, you can represent in certain ways. You're right. Yeah. That actually, I think they talked about in chapter 3. They did stuff like that. So that is one thing that we can, that's one way. So the short answer to your question is yes. That is one way to add vectors, but that's doing it graphically. What I'm building here is how to do it quantitatively, which is not quite the same. It's because here you don't.
I wasn't trying to argue with you or nothing. I was just saying actually it is, because you had just like used the associative property, which means you basically like foiled it. So you had to add them on the end. I'm sorry, just a little like me analyzing the data. That's just what I got. I wasn't adding it geometrically like you showed it in the example. But it all lines up. I understand. I probably shouldn't have said nothing, but thank you.
Well, yeah, you can say something. That's fine. Well, I mean, yeah, maybe you're right in a certain way. Let me say it a different way. Ultimately, if you're adding two vectors, you don't get a different answer. So however you add them, you get the same thing. So in that sense, which is I think you mean, yeah, it is the same thing. But what I'm trying to say is that there's certain mathematical ways you can approach it. You can approach it from different perspectives. And in physics and mathematics, we kind of break down a couple, three different perspectives. We can do something graphically, like how I showed you with looking at the area. That was looking at, basically that was the equation of motion, right? Like when I in the last example earlier in class, I asked you, if you calculate the area, does it represent something physically? Well, you can graph, and what you many of you correctly told me is that it was displacement. Okay, yeah. So displacement is displacement for a particular situation. But how do you figure it out? There's a couple ways you could do it. You could draw a graph and calculate an area. If you have enough information to do that, take the area of that curve and it gives you displacement. Or you can start with the equations of motion, which is what I did last week, manipulate the equations of motion and get the displacement. So yeah, you're right. In a general sense, ultimately you are doing the same thing, but you're doing it with different methods that look at it from different perspectives. That's what I mean. It's different. So the idea of adding vectors like you're talking about is probably the first way that we all learned to add vectors back in high school, right? We learned to do it this way. And I'll go over that a little bit later when we get to something called, I'm going to put it in the context of a physical concept called relative velocity. So we'll get to doing that. But here I'm trying to build a different perspective of it's the same thing, but it's looking at it from a different perspective. And it's really good that you see that, because a lot of people don't initially, that you can look at what I'm doing mathematically here and correlate it to adding, and these were called like the triangular method or the parallelogram method, or just in general, a graphical method of adding vectors. So that's really good that you actually see that doing this is actually the same thing as doing that. A lot of people don't, but they are slightly different methods of getting the same thing. So that's my point. And this is wonderful, but when we get to higher order problems, well, conventionally, we want to have, I don't want to say that, I want to try to, well, what I was going to say is that some mathematical methods are more powerful than others, meaning it's easier to use some mathematical methods to make computations maybe more efficient. I won't say easier, more efficient than others. In other words, I don't want to have to graph something every time I'm trying to find the displacement of something. So even though it's nice to know that graphical method and finding the area under the curve is displacement, I personally would rather have some equations that I can manipulate and, maybe get to it faster. This is the same kind of thing. Like I'm kind of building up some quantitative equations for essentially how to add vectors without having to graph them and do the triangular method or the parallelogram method. Even though it is still valid, and even though if you have that kind of brain, you can see that that's what we're doing here, even when we don't draw the vectors and draw it out. So that's the point. Okay. All right. So, yeah. So now that we have shown that quantitatively, I promised you I was going to come back over to this graph and show you where that delta R is, like what it looks like, because now we can see quantitatively that it's not the same as X or Y or even delta X or delta Y. It's related to it, right? Delta X is going to be, well, actually, let me show you all of it. So this distance is X1, this distance is X2. So what is delta X? Well, it's that minus that, which is this, right? So delta X is going to be this thing right here. That's delta X, okay? And delta Y is going to be this distance right here, right? So if I project this out over here somehow, right? Because it's this minus that, which just leaves this. So that's delta Y. And delta R then, it's kind of like, so the N is going from two positions, right? It's going from position this point right here is position 1, right? And this point right here is position 2. So you can think about getting from position 1 to position 2 a couple different ways. You could just go straight across, which he didn't do, right? That's the displacement, right? This is the path that he's taking, but the displacement is always defined as the shortest distance between 2 points. So the displacement is here. So that vector, and it always points in the direction of essentially the motion, right? So since I went from position 1 to position 2, that is the distance, the magnitude of delta R, but the direction is from position 1 to position 2, since that's the direction in which I was traveling. So this vector here is delta R, and it's not the path. He actually did this, right? But this is the displacement. So there's a difference, and they make a point about this in the book. There's a difference between path and displacement. Path is the actual distance that you move across. Displacement is the distance between the two initial and final points. So, for example, if I'm walking around, let's say I walk around like right now, I start right here, and I walk around a circle. Well, the path that I walk is the circumference, 2 pi times whatever the radius of this path is. That's clearly not 0. But what is my displacement? Well, my displacement is my final position minus my initial position. Well, this was my initial position. I walked around in a circle and I came up to the same point. So yeah, Kimberly, the displacement is 0. 0 distance, 0 meters. My path is 2 pi times the radius, or 2 pi or pi times the diameter. And that's not 0. I clearly walked along a path in a circle. So here in this example, the analogy of that is that the path length, you can clearly see it's longer than this displacement, right? Like if you added up all those, whatever that distance is, it's going to be much longer than the delta R. So the delta R represents the displacement, the shortest distance between the 2 points. That's different than the actual path. It can be, and in this case, it can be different than the actual path between the 2 points. And yeah, so you can see that if you brought this guy together with delta X and delta R, I can project it over here on the side because it's getting a little messy. You can see that it still fits the same kind of pattern. I'm gonna bring this over here. I'm sure get the same length. So maybe something like keep the same angle over here. Put it down like that. And you can see that it has a delta Y, which is, again, this distance here that I can bring over there. I'll do it in purple like I did before. And it has a delta X here. Delta X there and delta Y. So I can either go along positive, I'm at position 1. Did I miss a minus sign? No, I guess I didn't. Yeah, so I can move along. Yeah, right, -1. So how do I get to position 1? Sorry, from position 1 to position 2? I can move directly along R1 from delta R, excuse me, from position 1. Or, and what does this equation say? It says that I can move along R1 in the negative direction. So I can be at this point and move negatively along R1 and then positively along R2. And that brings me back to position 2 as well. And that's what this equation is saying. Move either along a positive direction, delta R, or move along -1 from position 1, negative R1 from position 1, and then along positive R2 back to position 2. And you can even see it here. Well, that's kind of breaking delta R down, but moving positively along delta Y, positively along delta Y, and then positively along delta X. And that gets me also from position 1 to position 2. A couple, 3 different ways of kind of seeing just essentially how you find the difference. You find the displacement, which is the vector addition of these two vectors, R1 and R2 respectively. Yeah, so any questions about that?
I do have one question.
Yeah,
On that last example, so our displacement is still, is it considered 1 unit?
it's not necessarily 1 unit, no. It
It's
can
not?
be not necessarily, no.
Okay,
It could be because I'm kind of talking generally here. I didn't put any specific values in, but I could do that and it probably would clear that question up. Let me make even more specific example.
oh,
So
okay.
let's come here and how can I do that?
No, I understand what
I'll-
you said. It depends on the data, like outside of the graph, right? It basically
What-
depends on the data outside of the graph. So if you had like data on Y and data on X, then that would tell us exactly how much displacement is in that instance, right?
Yeah,
If you had
yeah. If
number
I
values,
actually
yeah, okay. I understand. Thank you.
okay,
I didn't
right.
understand at first, but now I do. Thank you.
Okay, all right. Yeah. So then you don't need an example then?
No, I don't want to waste your time, class time. No.
It's not a waste of time. I actually have it in the notes. Sometimes I do, sometimes I don't. At some point I stopped doing it because I thought might not be necessary, but no. Sure, why not? Let's do it real quick. So, but yeah, it's basically what you said. You have data, but how would that look with respect to a graph? Um, let's come back here and just redraw. Well, might be able to superimpose it on top. Let's do something like this. So I'm going to go ahead and put in numbers. Let's make that 1. Let's make it black. Take like a number line. This displaced. Okay, yeah, let's do that. So one. Well, I want to do it over here because I need to add the vectors too, don't I? Yeah. So sure, why not? You know what? I'm gonna have to redraw this. It's not nothing. Yeah. Yeah. But I'm gonna leave that there. So if you have that, and redraw it over here. Okay. So do this. Okay. This just represents a regular, coordinates on an XY axis. And let's try to redraw that path. Oh. So the path, I don't know, I'm just going to sketch it in. So now it gives it some kind of, something like that, right? So we said the first position, I'm just picking some arbitrary points, just trying to make it. So we said something like right here, okay? And then the second point, I don't know, was probably like right here, okay? So we could sketch in the position vectors of those 2 points at 2 different times, just like we did before. But now we can quantify it, basically what you're saying, having the data. Right? But now I can take the data directly from the graph now that I know how to handle that data. And the data here is that position is just take it directly from here. I'm just going to extrapolate, right? Like, so that looks like it has X of, it's not quite 2, maybe 2.1. And then this guy is 2.4, 2.3. So the position, the first position, position 1, is going to have coordinates. Position 1 will have coordinates. What did I say? 2.1 x and 3.3 y. Let's just do 2 significant digits. All right. And position 2 is going to have coordinates we'll have to measure. So let's see. Yeah, it's about 4 for x and 2.2 maybe for y. Its coordinates are going to be 4.0 and 2.2. Okay, so now find the displacement. How would you do that? You'd basically stick it into this formula. All right. Well, this is it, but maybe you want to break it down like this guy. Right. So that'll give you the magnitude. And also, why don't you go ahead and, I didn't tell you how to find the direction, but I think you probably know the direction. And the direction is angle. See if you can figure that out. Like, what would be the angular direction? We can see that it's pointing down, so it's going to be in the, like if I projected this delta R back to the origin, it's got to be pointing down in the negative into the third quadrant. And that's going to be either, we can define angle a couple ways, either a negative angle or a positive angle, like if you open up in the positive x-axis in the counterclockwise position, that would give you something that is, I guess, more than 230 degrees. But again, just to test your knowledge and if you know how to figure out that angle, because we will go over that. We'll quantify that a little bit later. Right now, you don't really know how to do it. I'm just curious to know if you, given the components, if you would know how to do that. So go ahead, find the magnitude of the. What I have here. Find the magnitude of the displacement vector, and do it with. Give me the component method, which is going to be like this method here, but also give the magnitude. Like, see if you can figure out the actual magnitude and direction of that vector. So let me write it here. So for these 2 positions, find the displacement between positions 1 and 2. So find delta R between 1 and 2. But give and do it this way. Do it the component method. Or the component, representation, which looks like this. It's going to be like a vector R. R have its R X and Y components. Component representation. Then give me the magnitude. And then give me the direction. So you can remember that. And by direction, I mean the angular position relative to the x-axis, the angle that it makes with respect to the positive x-axis. WRT here means with respect to, of course, x-axis. Take a couple of minutes to do that, and I'm going to try to. We'll finish. So, in the interest of time, I want to, because I want to get these the parabolic motion equations derived before the end of class, so that you have it before the weekend starts. I'm going to move ahead with this. So, if I work this out, it would look something like this. Starting from equation 7 here. So delta R is going to be equal to x2 minus x1. So that's going to be 4.0, right? The x components minus 2.1 I plus y2 minus y1. So 2.2 minus 3.3. Oh, that's just 1. Didn't see that. No, it's 1.1. Works out. So the first answer here, the component representation, what is 4.0 minus 2.1? What is that? 1.9. I think. Yeah, 1.9. So plus 1.9 in the I direction. And then plus, so then you have 2.2 minus, but actually that's going to be negative, isn't it? Because 2.2 minus 3.3 is 1.1, minus 1.1. So minus 1.1 J. So that's the first answer. That's the position vector in terms of its components. So the component representation. Now, a little bit of trigonometry review here. Let's take this picture right here, because this is the best way to represent it here, this picture. And again, we will present this, differently and different, formally, and when we get to it in in a minute, but to kind of review some trig stuff. But this is a right triangle. The components of R, namely delta X and delta Y, make a right triangle in the vector space, in the two-dimensional space. That's this picture. What is a right triangle? It's a triangle in which one of the angles is 90 degrees. So there's going to be 90 degrees between delta X and delta Y. And you know it's 90 degrees because it's projected along the coordinate axes, and the axes are set up to be 90 degrees relative to one another. So you know that it's 90 degrees because of that. So it makes a right triangle. And we know, or you might remember that from your geometry, that with a right triangle, we can think of, let me blow this up, make it bigger. We can think of R or delta R as the, actually, that should be delta R, not R, sorry. I'm gonna make this bigger. Well, it's a triangle that looks like this, right? This was delta X, and this was delta R, or delta Y, and this is delta R. We have directions up with them, directions on. There. Delta R. We know that, and this is right triangle. So by the Pythagorean theorem, we know that the length of delta r is equal to delta y squared plus delta x squared, square root of that. You might remember that. Sorry. So recall the Pythagorean, theorem. So delta r is going to be equal to delta x squared plus delta y. Well, delta r squared is equal to delta x squared plus delta y squared. That's the Pythagorean theorem. But then when I take the square root of both sides, it becomes this. So that's that equation I would use to figure out the magnitude of delta r. So in this formula, then, and I guess I could represent it like that. So the magnitude of delta r can represent magnitude with absolute value signs. It's going to be equal to the square root of basically 1.9 quantity squared plus minus 1.1 quantity squared. And that's going to be equal to whatever it is. 1.9 squared, 1.1 squared, add them to the square root. Now, we haven't talked about rounding much yet, but I will get to, as I told you, I'm probably going to put up a thing on significant digits between now and Monday. Probably put it in module 1. But we're going to get something like 2.195 or whatever. If we round it back to 2 sig dig, which is what I'm going to do, so I'll put this 2.19 blah, blah, blah. Right? But if we're assuming that 2 significant digits, we're going to round it back to the 10th place. So how do you round? You go to the number above. If it's 5 above, so you're going to truncate, but then if it's 5 above the number in the 100th place, then you raise the 10th place one value, 1/10. So then rounded off is going to be 2.2. And that would be my final answer. That delta R is approximately 2.2. If, when I went to the 100th place, that number were 4 or less, then I just truncate it and leave it as 2.1. Yeah, so that would be the magnitude of delta R. What about the angle? Well, that's the direction relative to the x-axis. Excuse me. If I come up to this picture, now remember, I think I mentioned, let me mention again. If I take this vector delta R, and it's represented by a vector that looks something like that, right? I can take it and I can move it all over that delta space. I can do whatever I want, move it anywhere I want, as long as I don't change the angle, or, so that's direction, or change the length, contract it or stretch it, because that represents the magnitude. Since the vector has magnitude and direction, as long as I don't change the magnitude and direction, I can transfer it, to in any way that I want to make it easier to deal with. So I could translate this thing back down to the x-axis, to the origin, that is. Another way of thinking it from this picture, because I want to keep the picture, if I do that, then this vector is, from this picture, the x-axis is just the horizontal line at this point here, like that. So that the angle relative to the x-axis is going to be this angle right here. If I projected it down like so, you could see it there. So that's actually, when I say direction, that's the angle that I want. That's what that means. The direction relative to my coordinate system, and in coordinate system, the directions are usually measured relative to the positive x-axis. That's like projecting this guy down here like that. Okay. I'm going to use this picture. Now, that's the angle. Well, that's the direction or represents direction. But I can represent that angle two ways. I could do the negative angle, which it would be negative because it's pointing below the x-axis, or I could do I guess I could do this guy, you know, the angle. What is that? It's not complementary is 9 degrees. Supplementary is 180. I don't know what the angle is for making 360 degrees. The sum of the two. I forgot the name actually. You know, but it would be the angle that such that I would add to this theta such that the whole thing would be 360 degrees. Whatever. But I can get that here. I can get that with this triangle. So let me show you. Look at this. Let's use a little simple geometry. Let me erase this because it's a little bit. Yeah. Now, this angle here is 90 degrees, right? So I do know that this angle here, I'm going to call it alpha. Alpha plus theta is 90 degrees. So they are called complementary angles. Angles that add together to be 90 degrees are called complementary angles. Yeah, write that over here. I need space. Oh, I don't need this anymore. Complementary angles are those that add to 90 degrees. So alpha plus, yeah, whatever. You get it. Supplementary angles add to 180 degrees. While we're at it, let's go ahead and do this. Obtuse angles are greater than 90 degrees. Acute angles are less than, basically between 0 and 90. So less than 90 degrees. That's a few definitions. With a triangle, any triangle adds to 180 degrees. Keep it going here because this will be a little bit of a geometry for you. Triangles well, the angles of a triangle add to 180. Wait a minute, what? The angles of the triangle add to 180 or 360? 180, sorry. Triangle add to 180 degrees. And the angles of a rectangle add to 360 degrees. All right, so with that in mind, if we look at this triangle, alpha and theta are complementary because they add to 9 degrees. You can see with this corner here. But this is a 90-degree angle here. So if that is theta, and that is alpha, and theta plus alpha equals 90, and if the total angles of a triangle equal 180, then alpha plus 90 equals 180. Alpha plus, sorry, whatever this angle is, let's call it X, or I don't know. Well, whatever. You don't need to make a big, well, maybe you do. I don't know. Let's call it question mark. If this is true, that all of these angles add to 180 degrees, alpha plus question mark plus, well, we know that's 90 degrees, 90 degrees equals 180 degrees, then that must mean that alpha plus question mark equals 180 degrees. Sorry, equals 90 degrees. But if I already know that alpha plus theta equals 90 degrees, I know that from here, then theta is equal to 90 minus alpha. So this angle here must be theta. I don't know. I could have done that easier, but I don't know. Whatever. Yeah. So that this angle is theta is what I'm trying to say. Hopefully that wasn't too convoluted. But you might have to go through and think about that. But now once you got it, once you do think about it, then it should stick because you can kind of see it once you realize it. A couple other ways we could have figured that out, alternate interior lines and things, but there's, you pick your poison. That is, we could have extended this line here along like that and thought of this line as a bisector between these two lines. So if that's the case, you know that alternate interior lines or angles are the same. That is, that angle must equal this angle. And like if I extend this line along like this, we know that in geometry, you know that that angle there must be the same as that angle there. Sorry. No, it wasn't true. We draw this line down, this parallel line down to show that angle there is equal to this angle alpha, which means that this actually is alpha theta. So, you begin to kind of go through that and review that, and you begin to see it a little bit better. So that's also theta there, because those two are bisecting lines, but those angles are the same. But yeah, so there's a couple of different ways we can kind of approach that.
Yeah, they give us a formula for that one.
Say again?
I said they give us a formula for that one, though. Theta in that
Okay.
instance. They give us theta is inverse tan, delta y over delta x plus 360 degrees. That would give us theta in that instance. They give us
it
that
would,
in the book
actually.
too. Yeah, they give it to us in the book too.
Okay, good.
Yeah.
Good. Awesome. Yeah, it's a couple of different approaches to that. I probably will do a little bit more of a geometric review, but I wanted to just get that in right now because I was pointing that out. So yeah, probably could talk about sine and cosine, tangent, that sort of thing, just for a basic geometry review. Tell me that. Yeah, okay, 50, 35 minutes. So yeah, what am I doing? So yeah, so then the angle, so then you could use one of those formulas to get the direction. So yeah, let's do that. So because we want to know what the value is. And so yeah, I guess we could review it now, the sine cosine stuff. So for a right triangle then, if we know that this is theta here, then we could figure out what that angle is using our trigonometry. So yeah, the sine is defined as opposite side of a over hypotenuse for a right triangle. We can get that in. cosine is adjacent over hypotenuse and tangent is opposite over adjacent. So the general definitions here are the following. So sine of an angle is equal to opposite side over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And tangent of theta is equal to adjacent over hypotenuse. Cool. So, if I take this right triangle here, and I want to know, so now that I know that that's theta, and that, so I'm trying to find this angle, but I can see that that's also this angle. So I can apply it to this right triangle here. I mean, there's a couple ways I could see it. I could apply to that right triangle. I didn't have to do all that. I could have just applied it to this, because this is also, you know, the basically for the parallelogram method, the diagonal delta R is the diagonal of that parallelogram. So either way, I could do opposite over adjacent here, or opposite over hypotenuse here, or looking at it from this perspective, opposite over hypotenuse. It's going to give the same thing. But at any rate, and that's just one way to do it. I could do any one of these, right? Because I know all the values, all the length. Now at this point, I know all the length. But I guess technically speaking, delta R was an unknown. So what I did, the only thing I did know was delta X and delta Y. So in that case, I could just use tangent, because, you know, maybe I wanted to find that first, or maybe I only asked you for that and you hadn't calculated the magnitude of delta R yet. So yeah, if you wanted to do that, you could just use tangent. Tangent of theta is opposite over adjacent. So in this case, that direction theta would be, so if tangent of theta is equal to opposite over adjacent, that's going to be delta Y over delta X. So therefore theta is going to be equal to the inverse tangent of delta Y over delta X. The inverse tangent is represented as tangent to the negative 1. And this argument is going to be delta Y over delta X. So when I put in those values, what was my delta Y was 1.1. My delta X was 1.9. So basically, I want to figure out and I'm taking the absolute value of it. So I'm going to say that theta is equal to the inverse tangent of 1.1 over 1.9. So if I work that out, the calculator, so I get 1.1 into 1.9 inverse tangent. That angle is 63.3, well, rounded to 2 significant digits, which is what I'm taking. It's approximately 63 degrees. So theta is approximately 63 degrees. That's the final. So I've erased the question that I had over here. But that would do it. That the point slope formula was delta R is equal to 1.9I minus 1.1J. The magnitude is approximately 2.2. The angle is approximately negative 63, because the way I drew that's below the x-axis. So I could either give negative 63 degrees, or I could give a positive, was 63 minus 360? I don't know what that is. 297. So yeah, so the direction of delta R would either be a positive 297 degrees or a negative 63 degrees, giving the same direction of delta R pointing into the third quadrant. All right, so that's kind of an introduction to two-dimensional motion, I guess. There's a couple other things we could say. I should say it here, but I really do want to try to derive these equations before we get on to, and I can come back to this. I just want to give you tools that you'll have over the weekend. I don't want to wait. It's in the book, but still, yeah. So let me jump to that. I got 30 minutes. Yeah, gonna be a little tight, I think, but it's real good. So any questions about this before we leave this kind of introduction to the motion? 329, did I mess up? Or what did I say?
Well, yeah, they had us at actually so they had us at 360 degrees to delta y over delta x times inverse 10. That would give us 329 degrees.
I'm not seeing that. On the when you say they had you added, what do you mean?
Yeah, because it's like that in a book too. In some instances, they have us add
So here we go.
360 degrees. So it's like it's plenty. It's an example like that in a book too.
Yeah, so what I'm saying is that the angle, this thing, when you project it down, it's pointing down like this. I'm not sure what problem you're looking at, but what I was asking here is that, so when you projected that R down, it was pointing something like this, right? So there's a couple ways you can represent that vector. You can represent it by the angle with respect to the negative x-axis like this. So that's what I was calculating, and that calculated that to be 63 degrees. But 60, when you technically you define an angle relative to the positive x-axis, right? So I can say relative to the positive x-axis, that's pointing in the negative 63, negative 63 degrees relative to that. Or if I open up in the counterclockwise direction from the positive x-axis, how far do I go around? Well, that is.
And if you do that, then it is about 329 degrees. You see, because it's at about 330. That angle is at point at about 330 degrees. If you look at it from, because at X will be at 360, right? I'm just saying if we was looking at the unit circle, X would be at 0 and 360.
Yes.
So that angle is technically, it is pointing at about 330 degrees. If you just get your unit circle out and put it right next to it, that's where your point theta will be. If you set your unit circle right next to that. So they are right.
I thought that's what I was doing.
Yeah.
So if this is 63, then 360 minus 63, am I messing up? 360 minus 63 is how much? I get 297.
Yeah, I don't know how you got 360. Delta y, inverse 10 over delta y. I mean, theta equals inverse 10.
Is equal to 63. You don't see how I got 63? Is that not right?
No, I don't know. Let me
What'd
put
you
it
get?
back in my calculator. Let me put it back on my let me just put it back in real quick.
Because we said the delta y was 1.1. That's this distance here. That was delta y. And delta
No,
x
all the other
is.
data is correct, boss. I'm not trying to argue with you. All the other data is correct, right? The slope is negative 58. But in this instance, that angle is pointing at 330 degrees. Even if you put your unit circle right next to it, it'll give you it have it at 329.93. Because remember, we have to add 360 degrees to inverse 10 delta y over delta x. So when we set theta to inverse 10 delta y over delta x, then after that we add 360 degrees, and that will give us our total angle theta. There's plenty of examples in the book like that. So then our formula here will be inverse 10 times delta y over delta x plus 360 degrees. That will give us angle theta.
I think I disagree with what you're saying. There is a translation that has to, if I understand you correctly, there is a translation that has to occur whenever you're using the reference angle. For example, when I use that tangent formula in the first quadrant, the angle that I report as the official angle is the same thing as the reference angle. So like right here, if I had a vector in that first quadrant
then if I'm calling that reference angle theta, the reference angle, as I said, is always the angle relative to the x-axis in that quadrant. So when I use a formula like that for x and y in the first quadrant, basically that angle is just equal to theta. But if I'm in the second quadrant, well, this is the reference angle here. So if I want to report the angle relative to the positive x-axis, that guy, I have to subtract that angle from 180 degrees. So in the second quadrant, that angle is equal to 180 minus the theta.
Right.
In the third quadrant, that angle is going to be equal to 180 plus theta.
Right. And in the
In the fourth quadrant, it's going to be what you said, right? It's going to be, well, you can represent it a couple ways. The way I represent it is if you go all the way around, that's 360. But I'm not going all the way around. I'm only going this far. So you can represent that angle, this guy.
So even that would be 360 minus 30 degrees.
Well, it's not minus 30. It's minus this angle, what that I calculated. It's 360 minus theta.
Right, minus
That's
theta.
one way to represent it. Another way to represent it is just minus theta. Just like that angle is equal. You can also represent it as minus theta because the rule is you have to represent it relative to the positive x-axis. So I could just go in the clockwise direction and I got it, minus theta, or I could go in the counterclockwise direction and that would be 360 minus theta. Either way, they represent the same position in the angular, in the same angular position. So what I'm calculating theta to be is 63 unless I messed up. Because what we said was that in the component form, delta R was equal to 1.9x, or sorry, 1.9I, the x component, plus, what was it? Minus 1.1j. So in that formula, the angle is equal to the tangent of theta. The tangent of theta is defined as the absolute value of the y component, so delta y or y, divided by the absolute value of the x component, delta x in this case.
So that's where you made a mistake at. That's where you made a mistake right there, because you're actually supposed to set theta, and on the other side of the equation, you set your inverse tan next to delta y over delta x. Then you add 360 degrees, and that will give you your angle theta.
Well, this isn't a mistake. This is the definition of the equation. So once I solve for theta, that's taking the inverse tangent of both sides. So technically, if you write it all out, it's inverse tangent of tangent, because what you do to one side, you have to do the other side. So then you take an inverse tangent of this guy, delta y over delta x, right? So the inverse tangent of tangent brings out the argument. So that's how you get the theta. And then that's equal to what I think you said, which was tangent -1 of this guy. So I just started from the basic definition. So this is what I wrote over here. So now when I put in those numbers, that's what I did right here. You got inverse tangent of 1.1 over 1.9. And what I get is 63 degrees. I don't see, unless I put it in wrong, I don't.
Something is wrong. Let me see. Let me just look real quick.
So 1.1 divided by 1.9, you take the inverse tangent. I'm getting, well, I guess 62 degrees is what I'm getting now. What is it? 1.1, let's do it again. 1.1, enter 1.9 divided by, there you go. Now inverse tangent. Oh, maybe maybe I did do it wrong. I guess I did.
Yeah,
so I'm getting
that's
30.
I was trying to tell you.
I'm getting 30 now. Okay. All right. 1.1 and a 1.9 divided by, okay, you're right. I did. I made a mistake. So yeah, when you get out, you're right. I didn't divide it. So 1.1 divided by 1.9 gives 30 degrees right here. You're right. Awesome. All right, good catch. Thank you.
Absolutely.
So, yeah, so that switches it. So, basically, it's either negative 30 or 360 minus 30, which is uh 330, or yeah.
Yeah,
And what'd you say,
positive
329? Because I think I was off a point. You're right. Like, so
Yeah,
either
absolutely.
329 or whatever. Yeah, awesome, awesome. All right, where is that? So yeah, so either negative 30 or negative 29 or what, 31 or 329, whatever, because I think I had some significant digits off there. So
Yeah.
cool. Well, thank you, Kimberly. Thanks for the catch. Good
No
catch.
problem.
All right. Okay. Anything else? Any other questions or issues or questions, problems, troubles, gripes, as I like to say? Yeah, got it. Awesome. All right. Anything else? All right, let's move it along then. I got 15 minutes. What can I do here? You know what? I can do this the quick and dirty way. So I'm going to do it quickly, and then we'll go back and do a bit more comprehensive method on Monday. Let's do a quick experiment to set this up. I've got two objects. One, and we'll make them the same mass. 2 quarters. I have 2 quarters. Yeah. So can y'all see this? Can y'all see the 2 quarters here? See the 2 quarters? Now I'm going to have one on a ledge above the other, which I think you can see both from the camera. Yeah. Now one I'm going to take and I'm going to flick off like this, so that when I flick it, it's going now. Sure, I'm applying a force on it when I apply it here. You know, basically flick it so that it comes off with a horizontal velocity straight like that. But as soon as it comes off the plane, it starts to fall down because gravity pulls it down. But because I gave it a horizontal velocity, it falls what we say downrange from the vertical position of the ledge, right? If I just drop the thing from here without giving it a horizontal velocity, like we already talked about that. If I drop something, the velocity that it has as soon as I let it go is 0. We talked about that last week. And so it's not going to move in the horizontal direction. It's just free fall motion. It's going to drop straight down. And we did that problem on the first day. It's going to drop in a certain amount of time. Now, if I flick it like this, basically it's going to do 2 things. It's going to fall in the vertical direction, but it's also got to translate in the horizontal direction. When you put both of those motions together, that's when you get this kind of curved path that, as it turns out, is a parabolic path. Let me say this a different way. What if I were on ice skates and I came back over here, like I was on a flat surface of ice, and I flicked this object? If I flick it, it just starts to move along the horizontal direction without moving on the vertical direction because it's on a flat surface. And if this thing were an infinite plane, and if it were frictionless, like if I took all the friction away, if I were to flick it like that, it would move on horizontally indefinitely. Because in the vertical direction, I've got basically gravity acting down in the what we call a normal force. And we haven't talked so much about forces. We'll do that in a week or so when we get to Newton's laws. But basically, you have something called a normal force. Like when you're sitting down right now, gravity is pulling you down, but the thing that you're sitting on is pushing back with an equal and opposite force. It's Newton's third law. Well, that's why this thing is not moving in the vertical direction. Even though I give it an acceleration and give it a velocity in the horizontal direction, I haven't done anything in the vertical direction. So if this thing were frictionless, it would just slide on forever, right? Okay, well, when it slides off of the plane, there's nothing in the horizontal direction to affect that motion. It was going to still move in the horizontal direction, but there is something now to affect it in the vertical direction. Now the forces aren't equal. The reaction force, the normal force of the surface on the object is no longer there, but gravity is still there. So it's going to drop down just like it would if I dropped it from zero velocity. However, it still has horizontal motion. So that's why it moves with two motions at the same time, one moving down, one moving along, basically one accelerating down, as we showed last week, and one moving along at a constant speed in the horizontal direction. When you put those two motions together, you get that, right? So that's what this is. Now, I got a question for you. What if I look at both of these motions at the same time? Last week we showed, we calculated the amount of time it took an object to fall from a certain height. Now, when I give it a vertical velocity like this, or a horizontal velocity like this by flicking it, it's going to land over here somewhere. But if I were to flick one of them and drop the other one at the same time, which one would hit the ground first? In other words, would they take the same amount of time to fall to the bottom plane, or would one take a longer time than the other? By a show of hands, how many people feel that they would, well, just tell me, would they hit at the same time? Would the one that I flick hit later? The one that I drop, hit sooner? I don't know. Anybody want to respond before we do the experiment?
I think the one you flick will hit after the one you drop.
Okay, so Edgar says the same. How many people say the same? Can you use your like hand raising things there? So Edgar, and on the reactions, so I can see here. So 1, 2, 3, 4, Abdullah, Katie, Ike. Anybody else? Who's that? Joel. Okay, that's for the same time. Okay, Kevin Cox. Yeah. All right. Or Newful. Okay. How many people think that so that was the same time? How many people think that the one that I flicked would hit later? So hi, that's you, Hi. Okay. Anybody else? Abdullah, Ashuri, and Gabriella. Okay. And I guess we have a third option. How many thinks the ones that I drop would hit later? Anybody for that one? Nobody for that. Okay, let's do it. Try not to flick it so much so that it stays on the plane. In fact, I guess I could, yeah, I guess I have to do this. 10 minutes. Okay, so I guess you can also hear by the sound. Let's do. Do it a couple times. Yeah, it looks like with the sound, it looks like it's kind of hitting at the same time. Yeah, it's definitely better done in class. Could raise this, maybe lower it a little bit, give it a little bit more space. So you can still see that. Let's try again. That was a pretty good one. I'm getting the same time, right? Now, the answer is that they do. In ideal case, if I were to drop in a vacuum where there's no air, if I were to drop a feather and a Mack truck from the same height, or have one, maybe have the Mack truck rolling at some velocity. Well, I don't know, whatever. Objects, they will fall at the same. They will fall at the same. It would take the same amount of time to fall through the same height. Now, again, we'll focus in order to determine why that is. We have to really study Newton's second law, Newton's laws. That's in a couple weeks, but we can actually kinematically show equations that will illustrate that is happening. In other words, if you think about the motion, it's kind of what I just explained, that even though the one is translating has a horizontal velocity when it comes off, the motion in two directions are really separate motions. So gravity affects the one that is moving in a horizontal direction. It affects it vertically the same way that it affects the one that has an initial velocity of 0 in the y direction, because gravity only acts in the y direction. Like I said, if this thing were on a flat surface and I moved it along, gravity wouldn't, well, it's affecting it, but there's something countering gravity, which is the normal force, so it doesn't move up or down. But once that thing leaves the plane, the acceleration in the y direction is the same as the one I dropped, because the only force in the object in the y direction is gravity, and they affect the objects in the same way. And we've already determined that no matter what the mass of an object, if gravity is the only force that is affecting it in the vertical direction, then it will fall at the same rate. Now, these happen to be this very similar mass because they're both quarters, but that doesn't really matter. We've already shown that. What the issue here is, I'm trying to determine whether a velocity along the horizontal direction would affect the motion in the y direction. And experimentally, what we're seeing is that it does not. So let's assume that this is correct. We got pretty good demonstration, and that the object falls in the same direction, falls with the same amount of time through the same distance in the vertical direction. Now, if that's the case, we can basically almost write down the 5 basic equations for parabolic motion. Because if you go back to that chart that I wrote for you, the chart I kind of talked about at the beginning of class, we've got 10 equations: general motion in x, general motion in y, and free fall motion. Well, I've kind of given you a hint that clearly the motion of this object, the one that's translating in the y direction, what type of motion does it have in the y direction? Anybody?
Would it just be free fall?
It's free fall. That's right. And that's 4 basic equations, the ones that we wrote down. And Mikey, in the horizontal, I think you want to answer. In the horizontal direction, what type of motion does it have?
Oh, wait, are you asking me?
Yeah, who answered the question just now for me?
It was me. Mikey.
Oh yeah. Yeah, go for it, Mikey. In the horizontal direction, what type of motion does that one have?
I horizontal motion? I'm not sure like how to like
One directional or two directional?
General motion in the x direction, yeah, in the one direction. But based on those so when we looked at the general motion, we had constant motion, that was the first equation, and then we had the 4 accelerated ones for both x and y. So if this is the x and direction, you could kind of go to those 5 equations, right? The constant motion was x equals x naught plus vt. And then you had the 5 for the accelerated motion. V is equal to v naught plus ax times t and the other 3. So if this is x direction, if this is the x direction, what's that, Kimberly, involved? What is that? I'm not understanding that.
Oh, what happened? As you said, if it goes in the x direction, that would be all the equations that have x involved in them, right? Like in the cosine. The equations that you have to do with cosine or x, the value x inside the table, because we have a table for y and a table for x, right? It's kind of like out of the equations that you gave us. I don't have them in front of me. I'm just like going off what we were talking about last week or whatever.
Yeah, I'm referring to these equations. In the x direction, we had x is equal to x naught plus v x times t. And I said that was for constant motion. I think I called that equation 1. And then we had vx equals vx naught times ax times t was 2. And then 3 was x equals x naught plus vx naught t plus 1/2 ax t squared. And then 4 was vx squared equals vx naught squared plus 2ax times delta x. And then 5, delta x equals 1/2 x plus, vx naught plus vx times t. So yeah, that was one of the first column in that chart. So I had 2 other columns. One was the same equations that look kind of like that, but for the y direction. And then we had, just these 4 for free fall. So that's all the concepts in the kinematic equation that we developed. So yeah, what I was trying to say is that if you kind of break it out into x motion, the one that I flicked off, I gave it a velocity in the x direction. So the other equations in the y direction don't apply to that. And the free fall don't apply to that because that's also in the y direction, but a special case. So of all the possible kinematic equations that apply to that one that I flicked, it would have to at least come from these set of 5 equations. That was the point I was trying to make. And I know I said it kind of fast, but that's what I was trying to say. Now, of these 5 equations, this was constant motion. This was where the acceleration was equal to 0. And this was where the acceleration was not equal to 0, but it was equal to a constant. So I guess what I'm trying to say is that that object that I flicked off has 2 types of motion. One, Mikey basically got it correct, that it's free fall motion in the y direction. So those equations were for free fall. We have, v, basically these 4, but where this is negative g. So v, but also it's y direction. So using that notation, it would be vy naught minus gt, and then y is equal to y naught plus vy naught t minus 1/2 gt squared plus vx squared equals vx naught squared minus 2g delta y. And then delta y is equal to 1/2 vy naught plus vy times t. Now, those definitely apply. Mike has said that, but there's one more basic equation, and it's for the horizontal motion, which we call the x direction. So of those 5, which one applies to that direction? And the answer that I'm looking for is this guy. This equation would apply to the horizontal motion. Because in the horizontal direction, once it leaves my hand and leaves, once it leaves contact with my finger, and we're assuming no drag or no air resistance, there is no force in the horizontal direction that will cause it to slow down. So we basically have constant motion in the x direction and free fall motion in the y direction, and that's what causes it to call, you put those 2 things together, you get the parabolic motion. Now, there's one other thing that's very important to say, and basically Kimberly already said it. She said it implicitly. So let me go ahead and put this equation down, and these are the basic 5, but they're not quite the same as one dimension, because remember, it's 2-dimensional motion. I'm just using a basis of what we've already studied to kind of give us a jump into the equation. So I usually write this guy as 1, so I'm gonna write it in a specific order. And so for 2-dimensional or parabolic motion, we've got basically this guy, x equals x naught plus v x times t, and then we've got these other three, or other four. But we got to be careful. And this I'll have to, we'll have to pick this up on Monday. Kimberly was talking about sine and cosine, and it's correct, right? Like, we have to think about our geometry. Usually I don't use that example to represent it. More I like to think of maybe throwing a football or a golf ball, where we're starting off from the ground. And when we look at parabolic motion in general, because that was a special case, right? I was flicking it off of a ledge. But in general, when you throw something, it follows a parabolic path like that, right? And at every place along the path, the velocity is tangent to the path. So at the initial position, the initial velocity is a vector that does something like that, right? So that's V naught. But because it's two-dimensional motion, it has components, right? It has component V naught X, and the naught means initially at time. So Vx naught would be the X component initially, and Vy naught would be the Y component initially. So these are the basic equations, the form of the equations that represent the emotion. They're not quite the same as the one-dimensional case, because this Vx, let's make it Vx naught. That Vx naught, that actually equals V naught times the cosine of theta, where theta is equal to the angle that V naught makes with the x-axis. So that's what she was saying there in the response. So V naught times the cosine of theta naught. And Vy naught is equal to V naught times the sine of theta naught. Now, let's just stop there, because I think we ran out of time. But because we have these geometry relationships here, they make, even though these equations have the same form as the guys that we kind of took them from, they're not the same because of the two-dimensional nature of the motion that it's describing. And when we take the geometrical representation of the two dimensions, of the dimensionality, and put them in these equations, it actually makes them look quite different from those. And we can derive two others that I will on next week, call it the y of x equation and also the range equation. But that's important. I think it's important to see the symmetry, to understand that the functional form of the equations are related to the one-dimensional case, namely constant motion in the x direction and free fall motion. But because it's two-dimensional motion, we have to relate the motion in one direction to the motion in the other direction. And the way to do that is through the geometry that's actually describing the situation as well. And that's where you get the sines and cosines and tangent things from. And they change the fundamental nature of these basic like Vx and Vx naught. But we'll talk about all of that next week. I need a little bit more time. But hopefully that helps you a little bit to get into the two-dimensional motion and maybe start looking at some of the homework. But I'm going to go ahead and open up that homework so you can work ahead if you want. And also, actually, the lectures are there. You can find the lectures. I think I've labeled them two-dimensional motion already in the module, and it'll be there, and you can find it once you can find those once you open the module there. And it's clear about what day it's going to open. All right.
Thank you, Professor. Have a good weekend.
Okay, you have a great weekend. And be safe, everyone. All right.
Thank you.
Class dismissed.